For over a century, Einstein's general relativity has provided our most reliable description of how the universe hangs together. We visualize this as a continuous, flexible rubber sheet, where massive objects create smooth, curved indentations that guide the movement of everything else. But this smooth model fails at the quantum scale, where the math of continuity breaks down into a chaotic foam. To find a model that works at every scale, we have to look past the rubber sheet and examine the discrete structure underneath. The framework of quantum graph emergent field theory, or QGEFT, suggests that spacetime isn't a smooth fabric, but a vast network of interconnected nodes and edges. Here, thermodynamic optimization constantly rearranges these connections to find the lowest possible energy. This means space behaves less like an empty void and more like a dynamic structure that reacts to every movement occurring within it. This reactive structure functions as a learning system with a built-in memory, changing our understanding of how gravity actually works. When an object moves through this quantum network, the system's optimization engine lowers the local energy along that specific path. This leaves behind a topological scar, a persistent corridor of aligned edges that remains long after the object has moved on. These scars mean the network retains a geometric record of every physical event that passes through its bulk. When a second object enters this same region of the network at a later time, it encounters that pre-existing scar. The object glides into this etched channel because it is the path of least topological resistance, moving along the pre-optimized corridor with zero structural friction. This passive alignment through memory channels produces the predictable, stable trajectories we see in planetary orbits. In this model, gravity is the result of mass reading the geometric memory encoded into the network. But high-energy cosmic events, like black hole mergers, can force an object to violently veer away from its pre-etched memory channel. Moving into an unprepared region of the vacuum triggers a local optimization crisis for the network. The network is forced to sever established edges and rapidly restitch new ones to accommodate the object's unpredicted position. This rapid local reconfiguration of the graph's connections is the origin of cosmic stress. Restitching the network's geometry generates a surge of localized kinetic heat and structural tension. This excess stress travels through the quantum graph as a series of outward expanding vibrations. These vibrations represent the thermodynamic cost of breaking and rewriting the universe's memory. To see if this theory held up, researchers ran a large-scale simulation to see if a forced deviation would produce a measurable signal. This chart shows the results. At sweep 30, the exact moment of forced deviation, the top panel's edge force norm spikes, indicating massive stress release. The lower panels show the accompanying collapse. Acceptance rate drops, and graph distance from the original channel surges simultaneously. Without classical physics programmed into the system, this simulated stress radiation perfectly matched the 40.6 nanohertz background frequency detected by the Nanograph telescope array. This data alignment shows that a discrete network model can predict the same cosmological phenomena we observe through our telescopes. A moment of wonder. This shifts our perspective on space from an empty stage to a reactive, self-writing mechanism. It suggests the history of every object is permanently etched into the geometry of the present. Gravity is the result of the universe retrieving its own memories, and gravitational waves are the signatures of rewriting that history.